So for our first talk of the workshop, we have Fredrik Nordvall Forsberg, who will tell us about ordinal exponentiation in homotopy type theory.
Right, thank you very much. And it's great to be here, and great to see all of you here. Looking forward to this. So let me start by reminding you what I mean by ordinals, and then we'll get on to the exponentiation. So I'm going to be using the definition of an ordinal that you can find in the HoTT book, where an ordinal is defined to be a type together with an order relation, which is transitive, extensional, and well-founded. So transitive, you hopefully know what it means. Extensional is the axiom of extensionality from set theory, but we have replaced membership with the order relation. So we're saying that two ordinals are equal if and only if they have exactly the same predecessor. So if U is the predecessor of X, if and only if U is the predecessor of Y. So this gives us a way to show that ordinals are equal. And well-foundedness you can phrase positively in terms of accessibility, and an equivalent way to phrase it is to say that transfinite induction is valid. So if you want to show for all x p of x, then it's enough to show that, assuming that you already know p of I for all smaller y. Right? So that's one way to phrase well-foundedness. And I should say that there are many other definitions of ordinals that you might want to use in type theory, but here I would like to focus on this most general and, in some sense, least well-behaved notion. It's also the one that perhaps most directly is the same as the classical definition. Right? And the type of ordinals is itself an ordinal. This is the Brawley-Forty paradox, but here we can get away with it by saying small. So we have this size stratification. And how does it work? Well, we define the order on ordinals by saying that alpha is less than beta if alpha is a strict initial segment of beta. So there is some b in beta such that alpha is, and since we're working in HoTT, I can just write equals here. So alpha is the same as all the x below b in beta. Right? So I find some element in b, and then alpha is just the same thing as the things below it. Right? So that's a strict order. You can also define a weak order by saying that alpha is less than or I pronounce it less than or equal to, but it's not the same as less than or equal to. But alpha is weakly smaller than beta if alpha embeds into beta without gaps. So I have an order-preserving function from alpha to beta, such that if I find something below an f of x, or something below something in the image, then that thing is also in the image, and it's below the x. So I embed everything in alpha into beta, and I'm not leaving any gaps. Right? And with this order definition, you can show that ord is closed under suprema, so least upper bounds of arbitrary small families of ordinals. So if you have any family of ordinals, then you can always compute the suprema of this family. So one thing that you might want to do with ordinals is to do arithmetic on them. If you think of ordinals as a generalization of the natural numbers. So these are the equations you normally see in a textbook on ordinals. So you see that if you just read the first two lines, so alpha plus 0 is alpha plus suc of beta is suc of alpha plus beta, and alpha times 0 is 0, alpha times the successor is alpha times beta plus alpha, and the same thing for exponentiation as repeated multiplication. Then you just get the ordinary definitions you have for that defines addition, multiplication, and exponentiation for natural numbers, right? And then classically, we can just say, okay, we add one more line for what happens if we don't have a 0 or a successor, but we instead have a limit ordinal, or here I've just phrased it for arbitrary suprema, by saying that we should be continuous in the limits. So doing alpha plus a suprema of things should just be a suprema of alpha of all these things. So we're continuous in the second argument in the same way for multiplication and for exponentiation, right? But that's a valid definition if you have classical logic, because then every ordinal is either a 0 or a successor or a limit, but it's not a valid definition constructively, right? Because having that principle that every ordinal is a 0, a successor, or a limit is equivalent to excluded middle. So this is not a good definition constructively. It's not a definition, period, right? But it's a good specification because we know that if we define some kind of plus and some kind of times and so on, then we want it to be the same as the classical theory, and we know classically that this is the only definition that works, right? So classically, this is the unique definition. Constructively, we have to work harder to find something that satisfies this specification. And for addition and multiplication, it's well known how to do this. So, for example, for addition, you take alpha and you put beta to the right of it. So you're saying that you take the disjoint union of the carriers, and you say that everything in the left is smaller than everything in the right. And similarly, if you want to define multiplication, you can just take the Cartesian product of the carriers, and you order things reverse lexicographically. So you're saying that AB is smaller than A prime B prime, either B is already smaller than B prime, or they are equal, and then I'm looking at the first component. And it's a bit awkward that it's reversed, but it's because all of these equations are always looking at the second argument, right? So the second argument is more important. And then you can prove that you're given these concrete explicit definitions, and afterwards you can prove that these operations actually satisfy this specification, right? Because I don't have to do the case distinction anymore. I just have to prove each of the lines separately. And then if I wanted to assume classical logic, then I would know that I have the unique definition of addition and multiplication, right? So you could try to do the same thing. You can also prove other properties using these concrete definitions. So for example, this is a well-known property of ordinals, right? But you can also prove it constructively. So we say that if alpha is greater than 0, and you know that alpha times beta is the same as alpha times gamma, then we can cancel the alpha on both sides and just get that beta equals gamma, right? And it's important, of course, that alpha is greater than 0, otherwise this could be 0 and this would not be, right? And the proof is not completely trivial, but it's not so hard. But I just want to point out that if you just replace these ordinals with sets, then Andrews 1 has shown that already this implication that 2 times b is the same as 2 times c implies that b equals c is not constructively provable, right? By giving a countertopos where this fact is not true. So having the ordinal structure around really makes a difference, right? You can prove it for ordinals, but you can't prove it for sets. So this gives a quite roundabout proof that not every set can be well ordered, because if you could, then you could well order B and C, you would be in this situation, and they would be equal, right? So what about exponentiation? So we did addition and multiplication. It was quite straightforward. And surprisingly, at least to me, there is no nice geometric way to see exponentiation. So you could see the addition as putting one thing after another. You can see the multiplication as taking the Cartesian product. And you could think that, well, the exponentiation should be some kind of function space or something like this, right? But that's too big in general. So you can try to cut down this function space. And if you look in textbooks, then most of them just use the definition by transfinite by case distinction. But Sierpinski's textbook constructs a to the beta, alpha to the beta, if alpha has a least element, as the set of all functions, so not just the order-preserving functions, but all functions that have finite support. And the support of a function is defined to be all x that are greater, such that f of x is greater than the least element. Right? So we take all functions, but we only keep the ones that actually have finite support. Okay, and then the order on this is quite ugly. So we're saying that one such function is smaller than another one if f of b star is smaller than g of b star, but b star is the largest element where they disagree. Right? And we know that such a largest element exists because they had finite support. So eventually they will all just be the least element anyway. Right? But that's a terrible definition constructively. Right? I mean, first of all, we have to do quite a lot of work to even get here. And if you want to prove that this is transitive, for example, then you have to compare these two greatest elements and see which this one greater than that one, and then it just doesn't work constructively, right? So can we do better? So this definition kind of assumed that we had a least element, right? So let's focus on that case, and let's make it a little bit stronger. So we have a detachable least element. So alpha is of the form 1 plus gamma for some gamma, right? So we can distinguish the least element. And this is not such a big restriction, I think, because, for example, omega is the same as 1 plus omega. And, of course, 42 is 1 plus 41. So there's many examples of such ordinals, right? And they're not all just finite. Okay, so let's see if we can make the Pinker construction a little bit more intentional. So this is what we came up with. So we have ordinals gamma and beta, and then rather than looking at all the functions with finite support, we're looking at the graph of the function, basically. So we take all the lists of gammas and betas, and we say that these lists have to be decreasing in the second component, right? So we're thinking of these things as functions from beta to 1 plus gamma. So these are like input-output pairs. And if you're not in the list, then you're sent to the least element, right? And being decreasing in the second component, that means that every input has at most one output. And it also means that there's a unique representation, right? Because you have to be decreasing. You can't flip your things around in your list. So that's the idea. And then we can give this an order by ordering the lists lexicographically. And this time it's just ordinary forward lexicographic, not reverse. And then you can show that this is actually an ordinal if you started with ordinals, obviously, right? And just as a remark, if you don't insist on this decreasing in the second component, which means that it's decreasing overall, then you don't have a well-founded order. So if you just order lists lexicographically, that's not well-founded, right? But it is for decreasing lists. So we came up on this condition just to say that we can actually have the functions, but it's actually important to get an ordinal. So it's nice to see that playing out. Okay, and then you can show that this actually satisfies the specification for the exponentiation for 1 plus gamma to the beta, right? So how do you do that? Well, you look at the cases you have to prove. So for the 0 case, we want that 1 plus gamma to the 0 should be 1, but 1 plus gamma to the 0, well, that's a decreasing list of elements like this. So since this is the same as 0, it's a decreasing list of elements from the empty type, so the only such element is the empty list, right? So there's exactly one such thing. So this is really 1. And if we look at the successor case, this is what we want, that 1 plus gamma to the beta plus 1 should be 1 plus gamma to the beta times the alpha that we have here, right? So, okay, what's the left-hand side? It's a list which is decreasing in the second component. It's a list over these elements decreasing in the second component. So either the first element in this list is an in-right of something, in which case we have a gamma which we can send to the right here, or it's already an in left of something, and because it's a decreasing list, we can't switch back to being in right at that point, right? So then we have just a 1 here, and we are in this case. And in any case, if we take the tail of this thing, it has to be of the form in left all the way, right? You can have at most 1 in right in this list. So all in all, you get this equality, right? And finally, for the supremum case, I haven't shown you the details because this is the hairy case. But basically what happens is that it's really important that you're decreasing in the second element, because it means that if you have a supremum on the outside and you have all of these different lists, then you can always embed things into the type of the first element, because they are all decreasing, and the way the order is defined on the supremum is by being embedded into things. So I haven't shown you the details, but it works out. Okay, so we did the 1 plus gamma case, and you can also do the 0 case. So if you want to define 0 to the beta, well, we want 0 to the 0 to be 1, so we can't just say that this is constantly 0, but if beta is not 0, then we want it to be 0. So we just say, okay, lambda beta equals 0 satisfies this specification. So if beta is 0, then this is 0 equals 0, and ordinals are set, so there's only one such thing. And if beta is not 0, then the beta equals 0 will be empty. So 0 to the beta will then be 0 in that case. So it's not hard to show that this satisfies the specification. That's the easy case, right? So you could say, can we do this in general, alpha to the beta for arbitrary alphas? We've done it for 2 special cases, right? And the answer is that you can do that if and only if you have excluded middle. Okay, how does that work? Well, again, the easy case is that if you have excluded middle, well, then you either in this case or you're in that case, right? So you just use excluded middle to decide, and we've shown that it works in both of these cases separately. So the interesting direction is in the other way. So assume that you have such a function, and then because it satisfies the specification for suprema, it's continuous, which in particular means that it's continuous, which means that it's monotone. So now let's say that we want to decide P or not P for a prop P. Then by the specification for 0, we know that P plus 1 to the 0 is 1. And by the specification for successors, we know that P plus 1 to the 1 is P plus 1. And because of the specification for suprema, we know that it was a monotone. So we have this inequality in the middle. And so that means that 1 is smaller, is less than, well, 1 is weakly smaller than P plus 1, which meant that we have this embedding without gaps from 1 into P plus 1. And then we can just look at this function. If it's sending the unique element here to P, then obviously P holds. And if it's sending the unique element here to the right, then because there are no gaps, that means that P cannot hold, right? So that way, you derive excluded middle from these 3 things. And you see that by using all of the specification, which is quite nice, right? So to summarize, it's well known that ordinals are closed and well behaved under addition and multiplication. And you could think that this should extend to exponentiation, but it doesn't unless you have excluded middle. So the best we can do is doing these 2 cases separately. And you can look at our quite messy work in progress formalization where we have proved all of these things in Agda. Would like to clean up the exposition a little bit, but all the proofs are there. Right. Thank you for your attention.
Thank you. Any questions? We got some time. Come to
you. Thanks for the interesting talk. I had a question regarding the beginning about the uniqueness of the specification for the addition and multiplication. Are you saying that, let's say, in an interpretation, in, I don't know, some tuples or something, you have multiple notions of addition and multiplication that still satisfy all these cases? Or is this not the case?
I'm not saying that. I guess I'm also not saying that. In the sense, so what I'm saying is that classically, these things uniquely determine an operation, right? So you cannot prove that there are more than 2 things universally, but I guess there could be a tuples where you had different, I mean, something where function externality fails or something like this, right? So I don't know, it's an interesting question, but.
Yes, so don't you, I mean, I don't know, for me it's quite strange in the sense that in a way you, let's say, specify some, I don't know, things like addition and multiplication, you can define them as like using initial algebras and then faults and so on. So this is now something that you no longer have in this case, or?
Yes, indeed. So for the natural numbers it works because they are the initial algebra indeed. But the ordinals is not the initial algebra of this functor, right? You can maybe set it, but okay. So the hot book ordinals are not the initial algebra period, I think, constructively.
Okay, thanks.
Anyone else? We'll start with you, and then we'll pass down to you.
So just for 3 ordinals, you obviously can define this.
Yes.
So this shows also the difference between the 3 ordinals and these semantic ordinals, right?
That's true, yes. I mean, we already know there's a difference because the tree ordinals is an element of this, what you call semantics ordinals, these ordinals. So they must be different, otherwise they would, again, the ordinals would be an element of itself, right?
Can you construct in homotopy type theory an explicit example of an ordinal of which you cannot prove constructively that it has a detachable element? I mean, not being zero.
I guess even something like this p plus 1, you don't know if it's has a detachable least element or not, right?
Oh, okay.
That's the point. Yeah.
I mean, yeah, thanks.
Okay, last chance. Anybody? Okay, let's thank Fredrik again.